Good. Yeah, so welcome back to the afternoon session. Maybe not sure whether Amir said in the morning, but we try to devote the afternoons to be more high level than what we do in the morning, especially lighter on the details because it's been a full day. So let's try to keep this fun. The idea we had about today is basically that, well, still, you've maybe seen one problem which was not 3SUM-like in this bigger picture of 3SUM hard problems. So it would be cool if in the afternoon you could see a variety of problems which are 3SUM hard. And it's only fitting to talk about the 3SUM hardness of geometric problems because this is actually the original line of research on 3SUM hardness. It stems from geometric problems. Right, so let me give you like a quick overview. So there's a lot of papers which study geometric problems, and specifically this first one by Gant and Overmars observed for the first time that some problems share this hard core, which is 3SUM. And then only later, like you see all these papers would pop up here later. They're from like 2010 and onwards. They built on this paper by Patrashku, which incidentally is exactly the paper which introduced the convolution 3SUM hardness and the triangle listing hardness I've showed you before. And basically, then there was like this was a major breakthrough. And after this, a lot of other problems could also have been shown to be 3SUM hard, like dynamic problems, database problems, string problems, graph problems. So it really was a success story. But as I said, we're going to talk about the first paper today. So that's it. That's by Guy and Han Overmars on a class of O of n squared problems in computational geometry. They basically, well, it's two authors, but they acknowledged a lot of people from the entire computational geometry community. Really was a game changer. And the cool thing about the paper really is that while it had a billion results, all of them are really easy. And in particular, like all of the results can be shown basically in one slide. So the idea of this presentation is kind of that we're going to go through a lot of these reductions, and let's try and do it like quiz-like. Okay, so I'm going to show you a problem with its definition, and you can actually figure out in a very short amount of time how does the reduction work. So like the hope of this presentation is that it's actually just going to be fun. Not many details, just a lot of pictures. Okay. So specifically, this is the game plan for today. There's a lot of problems, right? 3SUM at the very top, and then we'll reduce to all of these geometric problems. Let's see. As I said, most of these are due to Guy and Han and Overmars. Some of them are due to this later paper. Still pretty classic stuff. Okay. Let's start. So this is the first geometric problem we have to consider. It's called geom-base, basically only because it's the base problem for all the geometric reductions that we'll see in a bit. And the claim is actually that this is, it's actually a subquadratically equivalent problem to 3SUM. In the sense that, one is in subquadratic time, then the other one is. So geom-base is defined like this. You're given n two-dimensional points that lie on three horizontal lines, let's say at the coordinates 0, 1, and 2. Okay, so these are the three lines on which you could have points. The question is there a line, a non-horizontal line, through three of these points? So for instance, this is indeed a yes instance because there's this line. This is a no instance because there's no way that you could draw a line through like three of them, right? Whenever you try to draw a line like this, you are going to miss these points. So that's a no instance. Okay? Question to you. Why is this 3SUM hard? Can you come up with a way? Like I don't really care about the other direction, but tell me how to encode 3SUM into this problem, to reduce 3SUM to this problem. I'm going to give you a minute. Wait, actually, let me wait 30 more seconds, but then I'm going to ask you. Wait some more seconds, but actually, I wanted to ask him first. OK, tell me. Sorry?
I'll pass this one off.
Oh, no, sorry. I meant actually, OK, no.
Think of the slope somehow.
The slope?
The slope of line segments between y equals 1, y equals 0, and y equals 2, y equals 1.
OK, good.
And then try to see where the slopes are equal.
That's basically a yes. Can you make it a little bit more precise? Not necessarily you, but like anyone?
A plus C minus 2B should be 0.
A plus B minus...
A plus C minus 2B should be 0.
Okay, sure. How do you want to implement that?
So like we say that 3SUM is equivalent to 3-colored sum.
Ah, now I understand you. You want to say like the x coordinates of these points are like A, C, and B or something like that? And yes, okay, very good. That's basically what you're saying. Yeah, I think let's just go with that. So what you're basically saying is, okay, let's start from a 3SUM instance, S, and we're going to add points to the geom-base instance, right? So we're going to add, for each element A in the 3SUM instance, we'll add a point at the first horizontal line at the x-coordinate A. Then we're going to do the same for every C in the, for every B in the y equals 2 coordinate. And then the same for C, but for C we don't place it at like C, but we place it at C half. Okay? Now if there's a line through 3 points, well then basically the point in the middle must be the arithmetic mean of the other 2 points. So A plus B half is C half. Equivalently, A plus B is equal to C. Good. Very easy, right? Now that's a cool problem because it really is equivalent to 3SUM. But maybe it's not a very natural geometric problem, right? Because obviously you started with a bunch of very weird assumptions, like the points have to lie on these horizontal lines. Then the output is not whether there is a line, but whether there's a non-horizontal line. So maybe the more natural problem to consider is 3 points on a line, right? Where the input is, again, you're given a bunch of 2-dimensional points without any constraint. The question is there a line which goes through at least 3 of these points? That reduction, unfortunately, is a little bit more complicated, but it's maybe the only one which is somewhat more complicated today. So for this one, I'm not going to ask you. I'm just going to show it to you. For the others, it's quiz time again, OK? So right, this is our problem. And the reduction looks like this. Again, we're given a 3SUM instance S. We want to place this instance as points somewhere. And the points we use is, well, whenever you had an A in your instance, you place it at the point A, comma A cubed, right? So x-coordinate A, y-coordinate A cubed. So you can see that all of these points obviously follow, this function graph of the function f of x equals x cubed. All of these must lie on there. Looks a little bit mysterious, but actually turns out if you now have 3 points, three points that actually do lie on the same line, let's say these, well, then, if you try to express that using exactly the same idea you said in the beginning, then basically the slope of this line segment is the same as the slope of this line segment. Or in math, that means, the slope of the first line segment is b cubed minus a cubed divided by b minus a. The same as c cubed minus b cubed divided by c minus b. Right? And now we're just going to take this expression and massage it a little bit. This is like maybe the most algebraic thing, not particularly intuitive, but it works out. So for first step is put some cheat fact to the top. X cubed minus y cubed actually factors nicely into x minus y times x squared plus xy plus y squared. So it turns out you can always just cancel the b minus a and the c minus b in these both 2 equations. Next, well, let's get rid of the b squared on both sides. So actually, it's just a squared plus ab equal to bc plus c squared. And let's rearrange it some more. So bring the c squared to the left side and the ab to the right side, and then it looks like this. Time for another cheat fact. X squared minus y squared is actually x minus y times x plus y. So again, you can cancel the c minus a from both sides because actually there's a minus, which you have to put here. OK, that's it. A plus b plus c is equal to 0. A little bit magically, but actually turns out if you put these points, there's a line through 3 of these points, if and only if there was a 3SUM solution. OK. Next problem. Damn it, I'm spoiling already. I didn't want to blend this in. OK. Well, the next problem is we've seen that 3 points on a line is 3SUM hard. A very related problem seems to be having a point on 3 lines. By the way, I should mention, for all the problems before, it's a fun exercise to also see that these problems can actually be solved in n squared time. which was pretty obvious before, right? Like to see that 3 points lie on a line, well, basically you always pick any pair of points, you check whether there's a third point lying on this line. Maybe you need some geometric data structures, but still. Turns out also this problem is an n-squared time, and the question is, why is it n-squared hard? Now, unfortunately, I cannot really let you think about it, but at least who has seen this point-line duality before? No one, really? 1, 2, okay. Some, okay, good. So it's this cool concept that if you start from, there's this duality thing, which, on the one hand, take a point in what I'm going to call the primal plane. Then you can rewrite this point into a line in the dual plane by the following transformation. So whenever there was like a point with coordinates a, b, you're going to replace it by a line which has this line equation, ax minus b. So you flip the y coordinate in a sense. Okay. Same holds if you have a line in the primal plane, say with this line equation y equals mx plus n. Then this corresponds to a point in the dual plane with the coordinates m minus n. Okay? And here's the fun fact. I mean, it's pretty obvious already from the picture, but if there was an incidence, like if there was a point line incidence in the primal plane, meaning in easy English, like the point lies on that line, then their dual objects have the same incident. So in particular, the point associated to this line lies on the line associated to this point. And if you want a reason for that, actually just try to do the math in your head, right? You want to plug a and b into the x and y coordinates here. So what's written here is b equals m times a plus n. And if you do the same on the right-hand side, then what's written here is minus n equals am minus b. So if you swap both sides, turns out they're equivalent. Okay. So now, if you consider the problem from before, right? The question, if there's 3 points on a line, that just translates exactly into 1 point lying on 3 lines in the dual plane. Okay, so by dualizing, you can actually show that these 2 problems are exactly equivalent. Just have to replace their points and lines respectively. Okay? Good. Let's get to some more advanced stuff. Visibility problems. So this is a more general class of problems which typically has the following flavor. You're given 2 designated objects and a bunch of obstacles in the middle. In this case, our designated objects are 2 points, p and q. And the obstacles are a bunch of opaque line segments, okay? Like, for instance, this picture. And the task is just, can p see q? Now, you can define it formally. Let's don't. It's very obvious what it should mean, right? Is for 2 points, does the line segment through these points not cross any obstacle? So what's your guess? What's the problem with this? Sorry? Someone said something? Linear time. Good. Not a hard problem at all. Why? Just check every segment. Yes. Good. So that's not a hard problem. What about this one? Point to segment visibility. This time, the same task, right? You're still given the 2 designated objects, but let's say this q is not a point anymore, but a line segment. And there's not like one line, but actually, you could see it everywhere. In the example, it's actually visible. What's your guess? Hard or not hard?
What does visible mean now?
So it means that p can see at least 1 point on q. I heard a bunch of answers. Who said still linear?
Maybe n log n.
Wow, you're good. Okay. Yeah, exactly. N log n. I don't know how, actually. Some geometric data structure stuff. I mean, basically, you can, like this region which is visible here, it's not too complex to express. I guess you can basically express it as like a polygon with at most n vertices or something. So with some fancy data structures, you can just test whether this line segment intersects that polygon. Let's go to one more variant, segment-to-segment visibility. Okay, so this time not p and q both are line segments. The question is whether some point on p can see some point on q. Okay, you seem to be in agreement it's a hard problem. Not even easy to verify that it's an n-squared time, but apparently you can do it. And you're right, it's 3SUM hard. So it really cannot be solved fast. So to you, those of you who said that it's hard, why do you think that? Did you see the reduction, or was it just because, last problem of the slide, obviously it has to be hard?
Feels like some kind of a convolution.
Sorry?
Feels like some kind of convolution because you kind of take points from opposite sides and you convolute them.
Yeah. Yep. I think that's a good intuition.
You can think of other line segments hitting B and Q, and then now there being like more number of points, like n squared possible.
Yes. Very reasonable. Goes in the same direction with the convolution. Yes. Go ahead.
I wanted to say that it is like choosing one point on the first segment, one point on another segment, such that no third point exists on the line between them.
Okay. So in that sense, it's similar to the geom-based problem from the beginning. Yeah, that's a good hint. So actually, what we should do is we should kind of reduce from geom-based to segment visibility. Now, how would you do that formally? I'm again going to give you like a minute to think about it.
What was geom-based?
Sorry?
What was geom-based?
Oh, sorry. Geom-based was this problem where you're given these points on these 3 lines only, and the task was whether there was like a line passing through, a non-horizontal line passing through at least 3 of these points. Exactly 3 of these. Feel free to discuss. Let's wait more like a couple more seconds. Okay, maybe you want to offer an idea first?
I think without lose of generality, we can consider all of the lines are parallel. So one of the segments we consider it as the main segment, and we can circulate all other lines and segments to become parallel with it.
So, right, just to be on the same page, right? You are allowed to pick the line segments, right? You're reducing geom-based into your problem, so you can pick the line segments however you want. In particular, if you want to pick them horizontally, that's perfectly fine. Right? So I'm saying we're designing a reduction from geom-based to segment visibility. In particular, you are allowed to build the instance. So you can choose the line segment basically however you like. Like, it's not even without loss of generality. You can just choose them to be horizontally. Right? Okay. I'm trying to find new people. Anyone wants to offer an idea? Yeah?
Build segments to fill all the gaps between the points.
Build segments to fill all the gaps. That's a very good first start. Okay, so you build a segment which goes right next to these points, but not exactly. There's some gap there. Good. Next step. Maybe someone else. Sure.
You pick your line segment P to be really long and horizontally at Y equals -1.
Good.
And Q to be at the top. And then they can see each other.
Perfect. Very nice. Like that. Okay. Yes, exactly. One has to be a little bit careful, right? If we would choose them a little bit larger, it would be an issue because then they could see each other like that. But if we choose them with the right borders, right, then turns out P can see Q exactly if there happens to be a line. Well, okay, first, of course, we get rid of the points. They're not part of the instance anymore. And then there's like, they see each other exactly if there was a line through 3 points. Okay. It's fun, right? Questions about this? Otherwise, I'm going to move on.
Have you seen the solution again?
Okay, so this was the construction, right? You started from the points. You added segments between the points, but so that there's still like a tiny gap. And you add the P and Q, the designated line segments in the top and the bottom, right? Now the claim is P can see Q exactly if there is a line through 3 of these points, right? And that's exactly the question for geombase. Not sure.
How big is this gap?
Yeah, okay, now you're asking the nasty detail questions. So, I mean, basically, you just have to work it out. Like, what's the biggest angle or the smallest angle you could choose here, and then you have to make sure that they're well separated. But basically, because you're allowed to play around with the numbers in an arbitrary way, so you can just first enforce that maybe the minimum distance between 2 points is 1, and then you choose the gap to be dependent on 1 and n. Other questions? Good. Next class of problems, motion planning. So the idea behind this is basically like the general topic here is you have some object and in like a source location, and you have a target location, and you want to move that object from the source to its target without hitting some obstacles. So think of like a robot, okay? So you have, in this particular problem, motion planning with translations, you're given 2 line segments, P and Q, where P is like the starting position of a robot, Q is the target position of a robot. The question is, can you move P to Q without hitting the obstacles?
And the obstacles are the line segments?
The obstacles are, again, just line segments, exactly. So in this example, for instance, you could build this maze, right? Like you have these walls. Questions, can P reach Q? Well, yes, you can follow this path, basically, right? This is the region which you actually traverse. Turns out this region does not hit the walls, so the answer is yes.
But isn't it kind of like some reachability problem? So kind of like reachable, but the width of the strip is always...
Yes, true. There's some sort of reachability question in there. Actually, in a very precise sense, like you can find like a free space diagram, I guess, whatever, for this problem. And the question is just whether there is a path through this which does not hit. Like, yes, true. So, easy or hard? Easy? Any other opinions? Okay, most of you seem to agree that it's easy. Indeed, it's correct. And log n. It's exactly what you've been saying, essentially. Like there is like there's a compact or like a good representation of the space in which you're allowed to move, and you basically just have to find a path through that feasible space. But it turns out to the key secret, the secret to success appears to be that there's 2 degrees of freedom, like translation to x and y directions, basically. Okay, so here's a harder version. So you're given still 2 line segments P and Q. You still have the same obstacles. This task is still the same, but we're not only allowed translations, but we also allow rotations. So in the middle of the line, the robot might rotate a little bit, then move on, maybe squeeze through a gap, and then rotate again. Okay, what's your guess? Hard. Okay, yeah, you're right. And really, this is because you have these 3 degrees of freedom. Okay. I don't know. I suggest that you have a look at the paper, though I tried that, and I was redirected a couple of times. I also wanted to know before the talk. Apparently, it's somewhat standard in this setting. The vague intuition really was that this feasible region can somewhat be easily expressed. Like I guess it's again just an n-vertex polygon in a sense. Where can you move with this line? And then you just have to check whether there's like a path through that in the end. Anyways, I can tell you about the 3SUM-Hardness reduction, but actually, why don't you tell me? Oh, wow, immediately ideas. Let me ask you first, because you already said something. Yes?
Exactly same thing.
Sorry?
Doesn't exactly same thing work? You want to get your line from the top.
Okay.
You leave the exactly same gaps that you can always come through.
Fancy, yeah. Was that also your idea? Yeah, exactly. So, okay, motion planning with line segments, right? We want to reduce from geombase. Geombase, again, 3 lines with a bunch of points. You want to ask whether there's like 1 line through 3 of these points. Now, they're much smaller because the R gadget has to be much larger. Can you be a little bit more specific? Which line segments, which obstacles should we place there? In between the points, good.
And
No worries. Anyone else? Yes?
But I want to make a big box so that you go and just like take it out from the side.
Perfect.
You have to go through the apps.
Exactly. Yeah, that's the one thing you have to avoid. Obviously, you shouldn't cheat. Exactly. And then, well, we just put the starting position somewhere in there. Exactly. Yeah, very, very subtle point. You have to make sure that these two are long enough so that you cannot... Let me, okay, first, to be on the same page, right? This is actually a correct reduction because, well, if this is the starting point, consider the following traversal, right? You start with P, you rotate a little bit, you translate a little bit, you go through exactly the line where you can go through, then you rotate again and you translate again and rotate again, right? So that's a way in which you could pass through. Now, your point was, well, you have to be very careful because if this line was too small, like let's say, small on this, you could just go in here, rotate a little bit, translate, and go through here or something, right? Cheating. That would be not allowed. So we make them long enough so that you cannot rotate inside of the regions. Okay? Cool. Next family of problems. Unfortunately, already the last one. So pattern matching. That's like a fun topic not only in string algorithms, but also on points. So this is called point pattern matching, also sometimes called the constellation problem. The idea is basically you're given two sets of points. P is like a constellation of stars. Q is like all stars in the night sky. The question is, can you find that particular constellation in the night sky? Can you translate it such that it's covered by the night sky? Sorry?
Without rotation.
Who's saying that? Without rotations. It's also interesting with rotations, but just for simplicity here, we just care about the translation of P. So in this case, the answer would be yes, because you can translate it like this, right? And then actually, there's the pattern. OK. Easy or hard? Yeah, less confident because it looks like a trap. Anyone wants to offer an opinion? Easy. It is indeed easy. This time, not with geometric techniques, though. This uses the fast Fourier transform. Sorry? OK. So what about this problem? Segment pattern matching. The task is still the same. You're given some objects, and you want to ask whether you can translate the objects to match the other objects, right? So this time, the constellation and the stars are not necessarily points, but line segments. OK, yeah, I think by now you understood the game. So yeah, this turns out to be 3SUM-Hard. The reduction is different, though. And actually, we're going to prove a direct 3SUM reduction, so not from geom base. Should I go back? Anyways. OK, so any ideas how this reduction could look like? I'll let you think about it for a minute or two.
And these trajectories cannot overlap, right?
I'm not sure I understand. What do you mean?
The trajectories when a point is moving towards another point.
All right, they all have to use the same movement, right? You have to take the entire pattern, move it simultaneously.
Oh, okay. So these lines are parallel.
Yes, they have to be parallel for this to make sense. Exactly. Sorry. Okay.
Actually, I have another question. So do the line segments have to be like exactly same, or can it be like?
They could be anything, but I think that you're having the same concern as her before. Like if, like in the pattern, you have a line which is like this, and in the night sky all lines like this, then the answer is obviously no, right? So it only is interesting if all the lines have the same orientation. Otherwise, you have to take rotations into account. The problem becomes much more difficult. So just for simplicity, assume all lines are parallel. Then there's no issue with this, right? But again, we're showing hardness, right? So you can just construct the instance to have parallel lines. This one's tricky. You have an idea?
Okay, so you're saying that this problem is the same as the point matching problem, but they could all be parallel lines of the same length?
Yes. Okay, I should not have saved from that picture. Yes, just think of the points as like, let's say, all of parallel horizontal lines, for instance. Question is whether you can move these lines such that they're all truly covered by the other parallel line segments. Does it make sense?
It's not covered, it can be a subset of the line also.
Yes, it can be a subset of line, exactly. Is the problem clear? I can also just draw something. Is it clear? Good. Okay, I'm going to give you another 30 seconds to think about the reduction. Then. Anyone has any ideas? Look like you might have.
Make the original, the bottom line segment of width C, or for each, I guess S, you make one set of them for every element.
Okay.
And then you set at like staggered heights, like different copies, and you try to see if there is a solution.
So you kind of want to make sure that. So for every element, you had a line segment of that length. Is that what you're saying? Then I'm a little bit worried that you might get false positives basically because you have, like, you can also cover, you want to say something like you have 2 points A and C and then a line segment of length B, so then you would have A plus B is equal to C, right? But then you could also have like a slightly smaller C and it would still be covered. The idea is very good though, like the distance of two things, maybe it shouldn't be like a line segment, but think of two very short lines at distance B, right? Then this idea actually makes a lot of sense. That will be used, but any more ideas, any more ingredients to this reduction? Okay, then let me, okay, do you have an idea? Yeah.
Is it true that you can use like AP plus BC equal to minus A minus B minus
Say it again, please.
So if you have segment sorry, I just feel you want some segments from 0, 0 to 80.
Okay. I'm going to continue a little bit, and then you're going to tell me whether that's what you had in mind, okay? So let me show you the first, like the construction of the P sets of the, the stars, the constellation set, and then maybe I'm going to ask you again about the other set. So let's start from a 3SUM instance, S, where all the elements are named B1 through Bn. And consider the following, the real line, and the relevant intervals here is like for, you have intervals of length 6u, where u is like the universe size of the 3SUM instance. And now we'll place a point exactly in the middle of these line segments. And then now there's the distance idea. We'll add a second point in every such segment at distance bi. Okay? So in the ith one, you added another point such that these have distance bi. Now, the idea, which you had before, right, was, well, maybe we should add also all the points in S as points somewhere. Then if there's a point A and a point C, then they can perfectly match these if and only if they form a 3SUM, right? If A plus BI is equal to C, then these 2 points A and C will cover that. But there's an issue, because we have to cover all these points, not just the solution point, without making the problem trivial. How would you do that? Yes?
Is there some idea of make a distinct row for each element?
Sorry, say it again?
To make a different row for each element?
That might help. Turns out you don't have to do it. Like the difficulty which you really have to face here is that, well, while we want maybe this one to perfectly match some points, you have to cover these somehow. That might help to use different rows, but there's like a more straightforward answer to how you could cover them. A really long line, yes, but you have to be really careful.
Not long enough to cover all of them.
Exactly, perfect. So you make it exactly long enough to cover n minus 1 of them, but not all of them. And then you also do it on the right-hand side, but you leave this tiny strip in the middle. Right? Now, if you check, right, you cannot cover all points with this line segment. You also cannot cover all of them. But obviously, you can shift them around arbitrarily, right? So you could put some points on the left. That would be stupid. You could put some points on the right. That would be stupid. The only reasonable option is to put some of them here, and have some of them in the middle. What's missing now? Any suggestions?
You have a segment of length A coming from the left and length C coming from the right?
Not a segment, because otherwise you have again the same issue. But let's say just points. Just we take the entire set S, and we put it in the middle, same as before. Now suppose that we could actually match these points, right? As before, obviously you have to pick one of these parts and you have to match them at the middle. If you want to match them, you should match them with some points in S. Okay, so what happened? All of these points, they're covered for free, right? The only thing which matters are those. And well, if you denote the left point by A, the right point by C, then exactly you have that A plus BI is equal to C. Right? Which is exactly the 3SUM condition. So depending on what is the B node, you determine like the global shift. Depending on the A and C, you determine like the local shift in here.
Oh, wait, you don't know which BI,
Right. But no. We're like, just construct this instance, right? If it was a different BI, let's say it was this one, then you would match these to the middle, this to the left, and those to the right.
but you don't know which one, so do you like go or
No, but like I'm just constructing the instance of the problem, right? The problem has to find the good shift.
Yeah.
And I'm saying like there is a good shift if and only if that is a 3SUM solution. Basically because we don't know what is the BI, but if I was to construct the shift, I would take the good BI and I would match it to the middle without knowing which is the one. Like not as the one who's designing reduction. For this, I don't have to know.
But what I don't understand is these line segments are fixed to long line segments. So now you would need to go crisscross, it won't be parallel. That's what I'm worried about. So for example, if you didn't choose this BI, and the first BI was the one you're moving.
Good. Oh, you have to move all points with the same shift, right?
Yeah.
So I take all these points and I move them in such a way that these 2 points are roughly here. Then all the others are covered by this line.
Oh, so you're using the fact that the others can actually, everything can be covered by the remaining.
Exactly. Exactly. These lines can cover everything except for one pair of points. This has to go into the middle. Okay? Everything clear? Feel free to ask. Okay. One final bonus reduction. There's another pattern matching problem. It's called polygon containment. So polygon is just, you have a bunch of vertices. Like we're on the same page. What's a polygon, right? A bunch of vertices, and you draw edges between them. The polygon containment problem is, again, you're given like a pattern P and some other polygon Q, and the question is, can you translate P such that it's covered by Q? Same as before, just this time we're not talking about line segments, we're talking about a polygon. This problem is also hard, and it follows somewhat trivially from the previous reduction. Can you see how? So don't even think about 3SUM, just think about segment pattern matching, the problem from before, right? The one where you have to translate line segments and so on. By the way, sorry, I forgot an important point here. Of course, we have constructed an instance which contains points. That's not actually part of the problem, right? The problem asks for line segments. So actually what you have to do is you have to like just turn these points into tiny line segments, right? Otherwise, it just doesn't type well. But it's a technical detail and doesn't really matter much. Good. So how do you turn the hardness of segment pattern matching into a hardness of polygon containment? Let's give him 1 minute, but then I'm going to ask you. Or is it a question?
Can I ask for the previous slide?
Sure.
The lines on the bottom.
Yeah.
So it kind of implicitly assumed that we can like partial match, and we don't have to match exactly.
Yes, you don't have to be perfectly aligned with the lines. You just have to be covered, right? As in, you have to be a subset.
I missed this one.
Okay.
It's crucial.
Yeah, that really is crucial. Oh, oops. What's your idea?
So I wanted to turn the lines into really thin polygons, but then
Okay.
I noticed you can only have one polygon.
Yes, you can only have one polygon.
And then I thought maybe you connect them even
Sounds good. It's basically the solution which you might have glimpsed at already. Sorry, you also wanted to offer something? Or was it basically that? Okay, but that's basically it. You just try to make it turn into a polygon. So you take a line segment and, well, those become like these teeth, right? And then, well, to turn it into a polygon, you have to somehow do something. Let's do this. And then it's like this key shape, right? If you can translate P into Q, well, then you can also make this this big subset of this polygon. By the way, maybe it's drawn a little bit like misleadingly, but obviously I don't think of this as like a filled region. Right? It's not just a boundary. Okay, good. Any final questions about this? Otherwise, let's wrap up. Yes?
I think I missed the part where you were talking about coverage. What do you mean by coverage translation?
Oh, it's just like the point where basically already about this problem. You know, if you want to shift them, it just has to be a subset of Q. It does not have to be equal to Q. It just has to be covered and not perfectly match.
Oh, okay.
Right. Okay. Any final questions about polygon containment or anything else? Otherwise, let's wrap up.
What was the translation of a polygon? It's just all the line segments.
Well, you can just take one polygon, right, and move it arbitrarily. So that becomes a subset of either one. Okay, good. Then, yes?
In segment pattern matching, all of these line segments don't have to be in the same line.
They don't necessarily have to. Turns out with this hardness reduction, you can just make them part of the same line. Like it's drawn as if they were two different ones, but you can just put them on the same line. So it's even hard just for segments of real numbers. Even one-dimensional, exactly. In the paper, they also talk about one-dimensional, but a little bit harder to draw.
For segment pattern matching, the line segments can have any angle.
They could also have angles.
So does the polygon always exist for these, the P line, line segment from P? Because I mean, like, you may not, I don't see how you can always construct a polygon.
Okay, so, okay, you're basically asking the same question. Like, you could even prove this hardness reduction just for one-dimensional segment pattern matching, and then you take that one-dimensional version and map it to the polygons like this.
Okay.
Right. Yeah, good point. Yeah.
Could you repeat again?
Sorry?
Could you repeat?
Sure. No. Yes, I was just saying, like, I mean, as many of you have observed, this is actually the same. Like, this hardness reduction even works for one-dimensional points and lines. You know, like it's not even about these points being in the plane, but actually you can choose like line segments on the real line, which is basically just intervals. And then for the second reduction to be formally correct, well, you have to start from the one-dimensional version. Otherwise, you cannot construct these polygons. You know, if you had lines which are arbitrarily, then why would you be able to construct them like this? Yes?
Do you ever use the geometric problems for non-geometric reductions, or is it usually easier to go through?
That's a good question. No, typically you reduce 3SUM to geometric problems, but I'm not aware of any reduction which takes a geometric problem to something else. We never view it as such. I guess, no, I'm also not aware of any applications where this viewpoint is helpful. But if you insist, of course, you could view it as a geometric problem. Yes?
What do we know about these pattern matching problem with rotation?
Good question. So for, right, if you allow translations and rotations, in one dimension it's a little bit boring, so let me talk about d-dimensional, maybe two-dimensional. Then the best thing we know is n squared, or n to the d. I'm not aware of a lower bound for this, though. That might just be because no one thought about it. I'm not sure. Maybe it's actually easy. At least the n squared might be easy. The n to the d lower bound is probably hard. Yeah.
Sorry, I'm still kind of confused about this. If the reduction is constructed like this, isn't this showing that 3SUM is reducible to polygon?
Yes, absolutely. That, like, I'm just showing you like the last step in the reduction is from segment pattern matching to this, but by transitivity of these reductions, turns out you reduce 3SUM to this, then to this. There's a reduction from 3SUM to polygon containment. But 3SUM hard, as we wanted. Am I misunderstanding the question?
No. So I was saying that we didn't act, by this construction, we can't prove that segment pattern matching reduces to polygon containment.
Well, you can prove that one-dimensional segment pattern matching reduced to this.
Yeah.
Yes, exactly. Put one-dimensional before there, and then it's okay. Yeah. I'm being and wavy here. Right? Yes?
When we say minus, since the reductions are like kind of not using the full degrees of freedom, is there reason to believe that they're not like completely tight lower bounds?
So for all the problems I've showed you here, they are tight just because there's n squared lower and upper bounds. For many of the problems, maybe you could prove even harder hardness assumptions. Like, for instance, if you start from an assumption which is weaker than 3SUM, maybe like hypothetically speaking, maybe from orthogonal vectors, an hypothesis which we haven't seen before, seen yet, but which we will see, maybe these problems are even hard for that reason. That might happen. I'm not aware of any of these problems to be hard for a different reason other than 3SUM though. Yes?
Do you have an example of where it's not just the same exponent, like in geometry?
Not for a geometric problem that I know. Oh, no, I do. Okay. Well, there are some versions of translational distances measures. Like instead of saying, well, you translate it and it matches perfectly, maybe you translate it, but then you just want to say that it's close to the object with respect to some distance measure. Typically, this is like the Hausdorff distance. For these problems, you often have running times of the form n cubed or n to the 4. And there are sometimes also matching lower bounds. They typically don't start from 3SUM, though. They start from quantified set or whatever. Other questions? We've finally long reached the wrap-up slide. This is just what we did today. I suggest, this was a lot of fun actually just preparing the slides. So I think it would also be very fun for you to, I don't know, just have a look at this paper. It's really cute. They have a lot of pictures, many of which I just copied. There's a lot of more papers on this, especially also some newer ones, which go beyond this, but I can really recommend. So, any other questions? Good.